Okay, I don't think I'm expecting more you to come. I have like 26 letters. So today we'll be looking at mixed strategy Nash equilibrium. We've been talking about pure strategies for far too long. So for the next 3 lectures, including today, we'll be looking at mixed strategies. And so today we'll be looking at what are mixed strategies, what is a mixed strategy Nash equilibrium. Next lecture, we'll be looking at some specific games where computing and existence of mixed strategy Nash equilibriums is possible. And in the third lecture, we will discuss about the general existence of mixed strategy Nash equilibrium in games and how we can compute them in general games. So, a brief recap of what we did till now. So we saw what Nash equilibrium was in pure strategies when each agent was playing one of the strategies available to them. Then we saw what is best response and how to compute Nash equilibrium using this notion of best response. Then we looked at what is a max-min value and what is max-min strategies when we focus on pure strategies. Similarly, this is a security notion. It always exists, independent of whether Nash equilibrium in pure strategies exists or not. But this is not an equilibrium strategy. It's just a security strategy that always is guaranteed to exist. And then we also have the min-max value, and which corresponds to the min-max pure strategies, and it also exists. And both Nash guarantees both of these values. So Nash guarantees both of these values, which is the max-min and the min-max value. So today, what we'll be looking at is mixed strategies. What are mixed strategies? We'll also see what is mixed strategy Nash equilibrium. And finally, there is a corresponding max-min and min-max mixed strategies. So this is the reading for today. Chapter 7 pretty much covers it all. And there are some nice interesting examples in chapter 4. So classic books tend to have nicer examples with more realistic real world. So that's the period when game theory was quite popular, like AI is today. So I guess which is the reason why there were so many books and they have thoroughly gone through the real world examples and everything. Okay. So we have graduated from prisoner's dilemma to matching coins. So in matching coins, what is the dominant strategy here? There's no dominant strategy. So what your strategy is depending on what the other agent is playing. So today the topic is existence of equilibrium, dominant strategy, equilibrium may not exist. Is there any possibility of iterated dominance here? Is there any strategy that is dominated? So whenever we talk about iterated dominance, we have to look for strategies that are dominated for any of the players. And then you keep doing that till you reach to one reduced matrix where you can then look for it. So that also is not possible in matching coins. So the third thing that we look for is the min-max values and the max-min values. So here the min-max, max-min will exist. And if you compute, I think the max-min value will be -1 and the min-max will be 1. You can verify that. So they always exist, and these are the values. And what is the pure strategy Nash equilibrium here? That also doesn't exist. So if you remember, in the last class we saw that, that the best response sort of formed a cycle. So whenever player 1 plays H, player 2 will play T. And now if player 2 plays T, player 1 will play T. If player 1 plays T, player 2 will shift to H. So there is no way that both of these players sort of converge to one set of strategy profile, which both of them do not want to deviate from. So there is no pure strategy Nash equilibrium in this particular game of matching points. So now what will you do? If I tell you you have to play this game, what is it that you will do? So let's look at one more game which is similar to matching points, and you guys must be familiar with it. This is the rock, paper, scissors game. So what is the strategy that you use when you play rock, paper, and scissors? You just randomly, I don't know how you randomize in your head, but you do. And then you play one of the options at random. That's what you do. So this is the matrix for that. There are 3 pure strategies: rock, paper, and scissors, 2 players. And if both of, I hope the matrix is clear. I hope everybody knows the game. So if both of them play rock, then nobody gets anything. It's a draw. So it's a 0-0. If player 1 plays rock and the player 2 plays paper, then the paper wins. It's 1 and the rock loses, so -1. If player 1 plays rock and player 2 plays scissor, so the scissor loses and the rock wins, so 1 and -1. And so on if you populate the entire matrix. So this is a zero-sum game. And if you can quickly verify also, there won't be any dominant strategies here. There won't be iterated dominance. No pure strategy Nash equilibrium. So what do is we tend to randomize in this game. Right? So in this game, it has 3 pure strategies. Let's say player 1 is playing random. It's playing randomly by uniform at random. So it's playing rock with 1/3 probability, P with 1/3, and S with 1/3 probability. If it does that, if you are the player 2, what would you do? So these are the random strategies I have denoted using this sigma 1. I'll introduce the notations formally again, but just once before. So SI is the pure strategy of agent 1, and sigma I SI denotes the probability with which agent 1 plays the strategy S1. That is sigma 1. So it plays R with probability 1/3, P with 1/3, and S with 1/3. Now, what my question is, what should player 2 do? Let's say player 2 plays R with consistent. Now player 1 is randomized. Player 2 plays R. So what is the utility that player 2 will get? If you remember utility theory, I guess not. So how do you, if there is a probability with which it is being offered these 3 outcomes, right? There are 3 outcomes. So since player 2 is fixing R and player 1 is randomizing between these 3, so player 2 is getting these 3 outcomes, and it is getting these 3 outcomes with 1/3 probability each. Okay? So what is the utility for player 2? How would you compute it?
Probability multiplied by utility of that player for that strategy.
For that outcome, for that strategy. So this is how it looks like. Now this you cannot arbitrarily do. It's because you are assuming von Neumann Morgenstern utility theory, and you have used the system of lotteries to elicit those utilities. You are able to use this particular form. This is going to be consistent because the agents are rational. Now, so the utility that the player 2 gets when it plays strategy R is 1/3 0, 1/3 -1, and 1/3 the utility of 0. Similarly, If player 2 sticks with the strategy paper, it gets 0, and if it sticks with strategy Caesars, it gets. Right? I hope this is clear. Now, if player 2 plays, so now it doesn't matter, right? All the three strategies is getting the same Euclidean. So will player 2 play only R? No, what will happen if he plays only R? Really? Why will player 1 keep randomizing? If player 2 only plays R, what will player 1 do? So now what is the utility it will get? So if player 2 only plays R, there is no incentive for player 1 to randomize. We assume that player 1 is randomizing. But if player 2 only plays R, there's no incentive for player 1 to randomize. Hey, what if player 2 plays R not with 100% probability, with some higher probability? Let's say 51 point some percent, 50 point some percent. What will player 1 do? No, even if you assign slightly, so it's always beneficial for player 1 to stick to some strategy, player 2 sticks to one of them. So now how do you ensure that? So what will player 2 do to ensure that player 1 randomizes? That's the question. We want equilibrium. We want a mixed equilibrium. We want that if player 1 is randomizing, so we want player 2 to play a strategy that ensures that player 1 is also random. Right? So this is what we will be answering today. This is what is mixed strategy in equilibrium. But before we do that, let me try to formalize what mixed strategies are. A bit of notations and things like that. So the mixed strategies are nothing but players playing their pure strategies with some probability. So given a player I with a set of pure strategies Si, a mixed strategy of the player I is a probability distribution over this set of pure strategies. And that is denoted by sigma I, which is a mapping from the set of pure strategies to 0 of the space 1, such that the sum is equal to 1. Right? Sum of all the probabilities is equal to 1. So this is how we define mixed strategy for each player. And is pure strategy also a mixed strategy? Looking at the definition. Yes. Because we have a closed interval. So the sigma could take a value 1. And if it has to sum to 1, then that means it can only play 1 of them. So pure strategy is also a mixed strategy. It's also called a degenerate mixed strategy. So I hope the definition of mixed strategies is clear. Next, we'll see how do you define the strategic form game when there are mixed strategies. So this is the set of all pure strategies available to player I. If that is what is there, so what is the set of all mixed strategies available to the player? How do we define the last set of mixed strategies from where he's sampling each of the mixed strategies? Now that is given. Now here, the player 1, the player I has M pure strategy, A, B, C, D, without conventional notations that we keep using. So there are M pure strategies. So the set of mixed strategies is drawn from something that is called a simplex, which is an m-1 dimensional simplex. And that the set of all pure strategies is denoted by this notation, which is capital delta Si. Have you heard of a simplex before? Okay. So the idea is, so if, let's say, the agent had only 2 pure strategies, right? Only 2 pure strategies, which is, let's say, H and T. Now, what it is trying to do is trying to assign some probabilities to. So, if it assigns probability P1 to H, then with what probability will it play T? 1 minus P. 1 minus p. So now what is the set of all possible mixed strategies? It's essentially any value of p it picks. Right? So it can pick a value of p from the interval 0 to 1. Right? And for every value it picks from this interval 0 to 1, there is one set of mixed strategies that it can correspond. Right? So when there are only two strategies, it is sampling from a one-dimensional simplex. One-dimensional simplex is nothing but a line segment. Okay. I hope it's clear. Now, if let's say the player has three strategies to play, H, T, P, something, right? Now you can just three strategies to play. Then it has essentially has to choose two different probabilities. It assigns P1 to H, P2 to T. So what is the probability with which it will play P? It's automatically 1 minus P1 minus. So now two-dimensional simplex. So it has to pick values P1 and P2 from a two-dimensional simplex, wherein P1 and P2 both are lying in between 0 to 1. So it will be simplex. It can pick values from any of this part. Is it clear? And the third is automatically. So this is a two-dimensional simplex. Similarly, if it has m strategies, so it will be an m minus one dimensional simplex from which it can pick a particular strategy and that will assign the particular mixed strategy. And this is the definition for a simplex. It's what an m minus one dimensional simplex looks like, which is all the possible strategies that it is picking from R to the n, such that each of them are positive, not strictly positive, and the sum is equal to 1. So this is how you define the set of all mixed strategies. Any questions?
This m minus 1 is kind of degree of freedom.
Yes, sort of. The parameters of this particular space.
Can you go back to that table, 3x3 table?
The rock, paper, scissors?
Yes.
Okay.
Now, here for player 2, maximum value is 1 only, correct? And that 1 is for all different strategies, RPS.
Yes, it depends on what player one is.
Yes, and that is why player 2 can play any of these. And that is player 2 can play any of these, because each of the columns has value 1 for player 2.
But if it plays anything deterministically, did he get 1?
Sorry?
If player 2 can definitely play any of the three, has three strategies, it can play any of the three, because there is no dominant strategy, so we can't say which. But if it plays one of them deterministically,
correct. Player 2 is fixated at one strategy.
If it commits to one strategy, will it do it? Will it commit to one strategy?
Not necessarily. Why? Because player 1 may not reciprocate accordingly, and player 2 might be at losing end.
Yes. So the idea is deterministic strategies are not going to help player 2. That's what I wanted to sort of explain.
But how do we fix the probabilities?
So I'll come to that.
Okay.
I'll come to that's the entire lecture today. So if I don't keep you guys hanging, you won't get into the notations, which is why I'm doing a mix and match. Okay, so then that's now that the notations are out of the way, we'll go to what is question is, how do you actually find the rank distribution? Okay, so this is the set of all possible probabilities that the player can assign, which is nothing but the set of all mixed strategies. And the game, therefore, now is N is the number of agents. Delta Si for each of the agent I is the set of strategies that now it can sample from. And then you have the utilities. Now, utilities have also to be redefined slightly, because utilities now is in pure strategy case, our utility was a mapping from the strategy profile, pure strategy profile to the real value. But now it will change to it's a sample, it's one of the samples from the mixed strategy profile to the real value. So that's how your utilities are now defined. And how will you calculate your utility? So the idea is for every strategy, every pure set of strategy profile that you sample, all these agents are independently picking their mixed strategy. Right? You just assume that they are independently. So what is the probability that this sample will occur? So if player 1 is picking, let's say, so out of the strategy profile, there is one strategy profile S1, small s1, small s2, small sn, that I'm picking that from this capital S1, whatever. So what is the probability of this strategy profile happening, given that agent 1 is playing this with S1, agent 2 is playing this with S2, sigma S2. So the product will tell you what is the probability of this sample, this outcome, right? So the probability with which this outcome will happen is sigma 1 times sigma 2 times sigma 1. So that's what I have put here. And with this probability, agent 1 will get the utility that corresponds to this outcome. Now, if I sum it across all possible outcomes, that is the utility that agent 1 gets in this. So for every, so because it's a mixed strategy equilibrium, and if every one of these strategies are played with some positive probability, then all the possible mixed strategy profiles will be happening. So they'll happen with this particular probability that is given here. So the agents will get utility corresponding to this strategy profile with this probability, and hence the total utility is sum across all the possible strategy profile probability lengths. Now this, we'll look at one example, it will be. So in the matching points, what is delta Si? How many strategies are there here? Pure strategies? 2. So how many, what would be the dimension of this simplex? 1. So what essentially each of these players are doing are picking one probability with which they'll play heads. It's a one-dimensional simplex. Let me sample one such mixed strategy, which is, let's assume that player 1 is playing both the strategies with probability half. Okay? And player 2 is also playing both the strategies with probability half. So what would be the utility of player 1? So if player 1 is playing both the strategies with probability half, player 2 is playing both the strategies with probability half, what is the probability that H and H happen? Half into half, which is 1 by 4. So player 1 is going to get 1 with probability 1 by 4. Similarly, every other strategy profile will also happen, the outcome, the agent will get this outcome with probability 1 by 4. So 1 times 1 by 4, minus 1 times 1 by 4, minus 1 times 1 by 4, and 1 times. That's the total utility that agent 1 gets when both of them are playing these particular strategies. Similarly, you can compute what would be the utility for the second player.
Ma'am, could you just explain what simplex was once again? I forgot that part. One-dimensional simplex.
So one-dimensional simplex is nothing but a line segment, 0 to 1. So if I take any value from 0 to 1, which is nothing but my value with probability with which I'm going to play h.
Okay.
It's nothing but sigma I h. So if I
Okay,
pick that,
got it.
that's the one dimension. So I can pick any of this value, which essentially defines the entire possible set of mixed strategies that I can.
Okay, ma'am, got it. Thanks.
Okay. So now we know what mixed strategies are, the space of mixed strategies are, and how you define utilities for each of the players when there are mixed strategies. Now what we have to define is what is a mixed strategy Nash equilibrium. Remember, the idea of Nash equilibrium is to prevent agents from deviating from unilaterally. So if I am playing a certain mixed strategy and you want the others to play a certain mixed strategy, they should not deviate from this mixed strategy given I am random. If I am randomizing, they should randomize with such probability. If they are randomizing, I should randomize. When will that happen? That's what we will see and thereby define what is a mixed strategy Nash. So let's first get the definition out of the way. It's similar to what the definition is in the pure strategy setting. It's just that, so given a strategic form game, a mixed strategy profile, which is sigma 1 star up to sigma n star, is a Nash equilibrium if for the agent I playing the mixed strategy, sigma I star, given that rest of the n minus 1 agents are playing sigma minus 1 I star, is the utility maximizing outcome compared to if he had used some other mixed strategy, sigma I, given that everybody else is still playing sigma minus I star. And this should be true for all the possible sigma i's, for all the possible sigma i's that I can sample from the simplex that I have, and this should also be true for all the n agents. So playing sigma I star, which is my Nash equilibrium, is the best response of sorts, given that everybody else is playing sigma I minus I star. That's one whole way. And that should be true for all the agents. This is what a mixed strategy Nash equilibrium. So let's look at this game, the coordination game. We don't have a dominant strategy equilibrium, and we have two pure strategy Nash equilibrium, which is either to play CC or RR. These are the two pure strategy Nash. Now, does this game have a mixed strategy Nash equilibrium? That's what we are trying to see. So the idea is, if let's say, if player 1 plays C, deterministically player 2 is definitely going to play C. If player 2 plays R, or one of them plays R, the other one is going to play R. There's no incentive for them to unilaterally. But now the question is, if I don't play any of these strategies deterministically, I randomize, what would the other player do? So let's fix a probability. Let's assume that player 1 is going to play C with some probability P, and therefore R with 1 minus. And player 2 is going to play C with some probability Q, and R with 1 minus. So now, if player 2 plays C with a probability Q, so now I have fixed probability Q here. If player 1 plays C, what is the utility that player 1 is going to get? It's going to get 2 times Q.
0.5 times.
Yeah. So here, so player 2 is randomizing with probability Q and 1 minus Q. So player 1 is going to get both of these outcomes with these. Player 1 is fixing C. So it's playing C with probability 1. So it's going to get both these outcomes, and it's going to get 2 with probability Q and 0.5 with probability 1 minus. So that's what I have written. It's going to, the utility is going to be 2 times Q. Similarly, if it fixes strategy R, if it's going to play strategy R with probability 1, again Q and 1 minus Q over here. So this is the utility, that is 0 times Q and 1 times 1. This is the utility. Now, if If U1 of CQ is greater than U1 of RQ, what will player 1 do? It will go for C, because given the randomization that player 2 is doing by picking Q, the utility that agent 1 is going to get by playing C is always more than R, then it will always play R. C. There is no incentive for it to randomize. Similarly, the other way around. If UR is greater than C, then it will always play R. Right? So what should these values be? They should be equal. Unless they are equal, player 1 is not going to randomize. So the idea is player 1 randomizes only when he's given that player 2 has picked the strategy Q. Player 1 will randomize only when these two utilities are same. So if we solve the equations, what we get is that Q is equal to 1 by 5. So if player 2 plays if player 2 plays C with 1 by 5 probability, then player 1 randomizes. Similarly, when will player 2 randomize? So you will have to recompute the same thing. So when will player 2 randomize? Player 2 again will randomize only when the utility that it gets by playing the pure, given that agent 1 is playing a pure strategy P, is playing a mixed strategy P, then if you solve the equations, I didn't write that. So ideally, if agent 1 is playing P and 1 minus P, so if player 2 picks C, given that the player 2 picks C, given that agent 1 is playing P, that will be given by just 1 P and 0 times 1 minus P. And utility when player 1 picks P and player 2 picks R is equal to 0.5 times P plus 1 minus P times 2. Now player 1, so to ensure that player 2 randomizes, player 1 must ensure that these two utilities are the same. So if you equate this, what is the value of P that you will get? 2 by 5. Sorry.
Whenever there is split, always one gets the probability of anything, and the second will always get 1 minus probability of that.
You mean the strategy? There are two strategies? Yes.
So there is two questions, and one is getting.
No, that is because the values are different. It is not always the case. Here he is getting 1 by 5 and this fellow is getting 4 by. That won't be the case always. We have to compute it. That's because the values are like that. Okay, we'll look at one more game. Yeah. So what is your mixed strategy Nash equilibrium in this case? So player 1 must play 4 by 5 and 1 by 5. Sorry. And player 2 must play 1 by 5 and 4 by 5. Right? What was the So a mixed strategy Nash equilibrium profile is governed by these probabilities. You'll have to, whenever I ask you what is a mixed strategy Nash equilibrium, essentially what you have to do is fix player 2's strategy, assume that he's playing Q, then when will player 1 randomize? For what value of Q will player 1 randomize? You have to calculate the utilities for all these pure strategies, equate them, get a single value of Q, and similarly do it the other way around. So you fix a value for player 1, and when would player 2 randomize? Using this particular equation, you equate it and then find value P. So only when these two players play these particular strategies, the other randomizes with the other particular strategy. Only then they don't have an incentive to deviate from these strategies. So that's how you compute mixed strategy Nash.
When we say randomize, that means it can choose any of the strategy irrespective of it giving any better outcome. So it is kind of indifferent between strategies, the other player.
it is indifferent between the strategies. But if it just plays anything at random, then why will the other guy random? So I am always trying to determine my strategy such that the other guy is indifferent between picking anyone. And similarly, the other guy is also determining his mixed strategy such that I am indifferent. Even though I am indifferent, I just won't go and pick any of these strategies because then the other guy will have an option to play deterministic. Won't play random. Get my argument? Yes.
And we could write the for each step as like a tensor product. So we take the outer product of all the simplexes on the
Okay.
layer and then multiply that with the tensor product. Right?
Okay.
So then it becomes like a minimal, the maximum with respect to one of
With respect to one.
linear.
So it seems like an easy thing to compute what the mixed. Sure. But the idea is But the idea is, what is the simplex that you need to choose? That's where the crucial thing will be, the major part of the computation. But will the players always randomize on all the strategies? No. What is the set of strategies that they will randomize? So we will look at that. That's where the heavier part of the computation is. We'll look at that. But you're right. So it's now it looks like a simple problem to get what the MSNEs are. Okay. So so the one online, is it clear now why, even though I'm making the other person indifferent, they won't just do anything because they have to ensure that I'm also indifferent. So let's look at one more game, which is the hawk and dove game. So there are two populations of hawk and dove, and these are the utilities that they get. If a hawk is fighting another hawk, they get 0 utility each. If a hawk is fighting a dove, a hawk gets a lot more utility than the dove, and if both the doves are fighting, it's essentially they fight, so they just stay peacefully and distribute the utility of 6 equally. So are there any pure strategy Nash equilibriums in this? If the population 1 tries to play hawk, what would the population 2 do? Play dove. If
Dove.
Yeah, hello. Yes, somebody is trying to speak. Yes. Population 2 plays dove, then what would population 1 do? Play hawk. So hawk and dove is a pure strategy. Similarly, I think dove and hawk will also be a pure.
Yes.
Okay, verify that. So now we want to find the mixed strategies. What would be the mixed strategies? Can you compute? So using the same approach, assume that population 2 plays with probability Q, and then you equate the values, you get some P, and you assume P here and get some Q, and that essentially will be your it's solving this, you will get Q, then equal P. So we'll do 5 times 1 minus P. solving this, you will get B. So you'll get 2 by 3 each. So they both of them will play off with the probability 2 by 3. So I hope how to compute P's and Q's are clear. So now we'll see one example. So reporting a crime. So typically when we see on the road there is an accident and there are a large group of people who are actually witnessing that particular crime or a crime, the accident or a crime, for example. Then what is the probability that the police is informed? What is the probability that one of the agents would at least reach out to the police and call the police? Okay. So there is a way in which I have defined the example. In this example, it defines the utility such that the outcome is not very nice. So the idea is that all of these people prefer that someone else calls the police because it's a crime scene. Nobody wants to get into the thing. So they want the call to. They want that someone should call the police, but they don't want it to be them. That's the idea. So we'll have some. If we want to write this as a game? This is how we'll do. There are n agents, and each of them has two strategies: either call or not to call. So what? Now we'll have to fix the utilities somehow. So this is how I fix the utilities. Just assume that the first utility here UI, when player I does not call and nobody else calls, the utility is 0 because it wants the police to be informed. If player I calls and it doesn't care, even if one of them calls, the police is informed. Right? So if player I calls and it doesn't care what the others are doing, it gets a value B because police is informed, but now it has a negative value of C because it had to call. So it's not very happy with being the one to call the police. Now, if it doesn't call, then there exists at least one other agent who has called, then this is the most happy situation. Somebody has informed the police and I am out of the story. So it gets the maximum value, that is B. So note that B is strictly greater than C and is strictly greater than 0. So it is strictly beneficial for me that somebody else calls and I don't call over me calling. And I also don't want this particular outcome where nobody calls. This is how the utilities are defined. Now, what does this game have any pure strategy Nash equilibrium? Let's analyze one of the instances. What if everyone calls? Is that a pure strategy Nash equilibrium? Is there any incentive for the other agent to deviate? So if everyone is calling, even if one of them doesn't call, then they will shift to this particular profile. And from B minus C, they'll get a value of B. So they'll get a strictly higher value. So if everyone calls, there is incentive for all the agents to deviate and not call. So that's not Nash equilibrium. Similarly, if no one calls, is it a Nash equilibrium? Because even if one of them calls, they'll get a strictly better outcome of B minus compared to 0. So what will be the PSNEs? So I have already given the answer. The pure strategy Nash equilibrium, there are n pure strategy Nash equilibriums in this game, where only one of the person calls. So yes, now.
Yeah, ma'am, can you please explain that everyone calls part once again?
So if everyone calls, everybody is getting a utility of B minus C, right? So
Yeah.
this particular utility is for all. Everybody is getting a utility of G minus C. Now, if one of them decides not to call, let's say agent I decides not to call, what would be the utility of agent I?
V.
V. Right. Because at least one other agent is calling, so agent I is happy. So previously it was getting a value of B minus C. Now it's getting a value of B. So will agent 1 I try to deviate?
Yes.
Right. So which is why this is not a pure strategy Nash equilibrium, because each of the agents have an incentive to deviate.
And in the third part, I think it will be where only one of the person calls. I believe that might be a
Where
typo.
only, sure, thank you. Where only one of the person calls. Okay, why is that a Nash equilibrium? So when only one of the person calls, if he chooses not to call, what would be its utility? Not to call. Nobody is calling. He is the only one calling right now.
0. 0.
0. So when nobody else is calling and I am the only one who is calling, now if I choose not to call, nobody is calling. So 0. If one of the other agents are choosing to call, what would be now? So except me, if I am the one calling, what is the utility of all the other agents? It's V. If they decide to call, given that I am calling, what would their utility become? V minus. Will reduce. So even if I change my strategy from calling to not calling, the utility will reduce. Even if the other agents change their strategy from not calling to calling, their utility will reduce. So this is a pure strategy in action. No, none of the agents have an incentive to deviate from this. So there are n such pure strategy in action. But now what we are trying to look for is a mixed strategy in action. So this is the explanation. He or she does not call, the value declines to 0. So now we are trying to find what the mixed strategy in action is in this. Let's assume that yeah.
Ma'am, can we revisit the previous one quickly?
Yes.
So here we have n people, and for each person, the strategy is either to call the police or not to call the police. Correct?
Yes.
Now what is this UI? Everybody is not calling equal to 0.
Yes.
I mean, this UI is for particular person or what?
Yes, UI is for I.
So ith person, I mean, everybody is not calling the police. So in that case, value for any person will be 0. That is what it means.
Yes, for all the I's, it will be 0 because the police is not informed.
And what is the next one? UIC dot.
This means that if I am calling, if I called, okay, I don't care what the others are doing. Now you can populate the rest of the vector with any values. It doesn't matter, C, DC, any
I mean, either C or DC. Okay.
either C or DC. It doesn't matter. As long
Yeah,
as
the ith person chooses to call. Okay.
If the ith person chooses to call, the utility of I is V minus C. It
Now,
gets
what is V and what is C?
So it gets a value V because the police is informed. But it gets a negative value C because it had to call. So there is a cost to calling.
Okay.
Because it's a crime scene, you don't want to get involved. So you assume that there is a cost to the fact that you're calling.
Correct. Yeah, I mean, many stories can be built around this. So, and then the strategy of UI, the other one, when everybody is not calling and only the ith person is calling, in that case, the value is V.
No. When I am not calling, value is V as long as the police is informed, right? So the idea is one of the agents has called. So the police is informed I'm getting a value V. And I don't also incur the cost because I'm the one not making the call. So I don't call, but somebody else has called. So I'm getting a value V.
Okay. Now, when everyone is calling, including me, then how it is PSNE?
No, it's not PSNE. When everyone is calling, it's not a PSNE.
Yeah, sorry, not a PSNE.
That is because even if any agent, let's say everybody is calling, right? C. let's say ith agent decides to deviate and not call.
No, but okay. But initially everyone is calling and then suddenly the ith person starts deviating. Okay.
If it is, so in this particular profile, when everybody was calling, what was the utility that ith person was getting?
Everyone is getting V, no?
No, V minus C, because they are calling, right? There is a cost to call.
Oh, okay, sorry. For person it is V minus C. Yes. For everyone it is V minus C.
Let's not talk about everyone. Let's just talk about I. Yeah. The first agent or the ith agent.
Okay.
The value is V. Now that the ith agent has decided not to call, but rest of them are calling, what would be its value?
Then it will be V because police has been informed and it didn't have to do anything.
Has it increased?
Yes.
So that means, will the agent deviate?
Yes, it will give a higher value V
Yes.
by deviating.
Therefore, it is not a pure strategy.
Okay. And when only one of the person calls, then there will be NPSNE. How is that?
No.
Because I can iterate from person 1 to person N.
So NPSNE is like this. When I call, nobody else calls. When the second agent calls, nobody else calls. Like that. So you have N different profiles which are pure strategy Nash equilibrium.
Correct. Different vectors, so to say.
Yeah.
Okay. ma'am.
Should we move ahead with big strategies?
Yes, ma'am. Please.
Okay. So to compute mixed strategies, let's assume that I fix some probability PC with which they are calling. First, let's see what is the utility if I call. No matter what the probabilities is, as what the other people are doing, as long as I'm calling, I'm getting this UP, P minus C with fixed probs. It doesn't matter what the other. But if I don't call, there are two ways in which I split the utility. If I don't call and no one else calls, except, apart from me, then I get a probability 0. But if someone else calls with some probability P, I get a value B. So this is the utility that I get. Right? Yes. It should be. I'll come to that. So the idea is that also serves as a sort of a symmetry in the game because it doesn't. So equating the so the idea is we want this particular agent to not to randomize. Right? So if it plays C, it gets this utility. If it doesn't play, it gets this utility with these problems. Now, if you want to equate it, what will happen is the probability that someone calls will be equal to V minus C by C. Right? If you just equate those values. So what is probability that someone calls? It's nothing but 1 minus probability that no one else calls. That's equal to this. So probability that no one else calls is C by V. And since we have assumed that everybody's probability is the same, so probability that no one calls, and that is PC is the probability that they call. So 1 minus PC to the power n minus 1. This is the probability that no one calls. So from solving this, we get PC as this particular value. And what would happen with n, when n increases, what would happen to PC? Go with the ratio n.
That's why it becomes smaller and smaller. We see like V minus C.
Again. Go and work out the math. As n increases, PC will decrease. The probability that you call will decrease. Go and work out the math. So probability that no one calls is nothing but probability I does not call and probability that no one else apart from I calls. So what is the probability that no one else calls? It's a constant. It's a constant C by V. It's independent of the probability. So the second term is constant, and probability that no one and the probability that no one falls will increase as n increases, because as n is increasing, PC is decreasing. Right? So probability that no one, so your PC is the probability that probability of you falling, and as your n is increasing, your probability of falling is actually decreasing. So probability that no one falls will increase as the number of agents are increasing in this particular group, since this is a constant. So now the idea is that in a larger group, larger the group is, the probability that no one falls will actually increase.
This UI do not call, the third line is equal to 0 times probability no one else calls plus V times probability someone else calls.
Yes.
So why this no one else calls is coming and 0 is the there?
You can have it also. That's fine. The idea is that when nobody calls and you have not called, you're not getting any utility.
Correct.
That's what I have represented. You don't really have to put it.
So that dot will be kind of including the scenario that everybody is not calling the police.
Yes.
And dot can be like there other scenario in which I am not calling, ith person is not calling, and someone, at least one person is calling the police.
The idea is these are mutually disjoint events. Either someone else is calling or nobody is calling. Right? So there are two disjoint events. When this event happens, I get 0, and when this event happens, I get V. That's what I mean.
Correct. And in that case, so what do we mean when we say equating the error? What are we equating?
So my utility is for two strategies. I have two strategies, C and DC.
Correct.
If I play C, I get a utility of V minus C, and if I play DC, I get this particular utility. Now, to calculate mixed strategy, the only reason for me to randomize is when both of these are equal.
I mean, both UIC and UIDC is equal.
Yes.
Okay.
So when you equate it,
That gives us P someone else calls like V minus C by C.
Yes.
Yes, okay. And P no one else calls.
Is this?
How is this coming?
So because of this. Because the probability that someone else calls is equal to 1 minus this. So if you do 1 minus of that, you'll get C.
And why the power is n minus 1 for 1 minus PC?
So what is the probability that somebody calls? It is PC, right?
Yes.
I have assumed that it is PC.
Yeah, that is the first time. Yes.
He does not call is 1 minus PC, and there are n minus 1 such agents who are not calling, because no one else apart from I calls. So
apart from me, correct. Okay.
This is the problem. Is it clear?
Yes, ma'am.
Now, probability that no one else calls is a constant C by V. And probability that I does not call is 1 minus PC. So 1 minus PC increases as n increases.
The probability no one else calls, we established this formula, no? 1 minus PC.
This formula, but it is, if you see, it's this formula, whatever it is equal to a constant C by V. So C and V are fixed in the game.
Correct.
So that's a constant. So your PC will change based on that, but probability that no one else calls will be fixed.
So PC is something like we can change according to our
According to your model, yeah, your game parameters, your values.
okay, cipher parameter. Okay. So, but whatever we do, it will remain C by V only, no?
This probability will remain C/V. But what we want is that no one calls. This is different from no one else calls. Sorry for these names.
Okay, no one calls. Okay.
Now that will increase because the probability of me not calling increases as. So whenever I see a lot of people, the moral of this story is whenever I see a lot of people, I won't really call because I assume that there are so many people they won't call, and this is what everybody will think. So the probability that no one calls will also increase. So the police is not. That's what we are. It's a very intuitive thing. We are just doing a lot of circus for that.
So the larger the group, more likely that no one calls,
Exactly.
which is quite correct.
Okay. Let's go to the computation part of the Nash equilibrium. I hope the example is clear. If there are any more doubts for the example, multi-agent systems behave like this. Well, I mean, if the utilities are like that, if the agents are rational, if they are intelligent, they behave like that. So we say
If that was the case, Preetu, then in the first lecture, ma'am had told regarding multi-agent drone system. No one would like to fly.
oh, we don't know. I mean, you'll have to tell me what the utilities are and everything.
Exactly.
And then we are only seeing at games which are all played simultaneously. That's not how we do it in real world. There are people who cooperate. This is all non-cooperative. So in general, we can't really make any comment. This is a very, very, very specific setting that I'm talking about. Okay. So now my question is, any more questions about the game? I'll take later. So let's move ahead a bit. So now my question to you is, I give you a guarantee that the mixed strategy Nash equilibrium will always exist. I'll just tell you, I have a two-player. Is it easy to compute the mixed strategy Nash equilibrium? Seems like it's easy, right? If it's not, why is it tough? Easy to compute, I mean, can it be done in polynomial time? Or will it take exponential time for you to compute?
Distribution.
Based on the distribution? So there are n agents. How many equations will you get? No, you have to think about it. And all are linear equations. They're all linear equations. Just solving some set of linear equations. How hard can it be? So what is so if I give you a linear, have you all done optimization? So what is linear? If I give you a linear program, some linear objective and linear constraints, could be, I should know the exact polynomial. Is it polynomial? Your claim is it's polynomial. Anybody else who claims polynomial? Oh, so my question, back to my question. If I give you a linear program with a linear objective and linear set of constraints, what is the complexity of that? Like how much time will it take for you to complete? What is the time complexity? Big O of n. Linear time हो जाएगा पूरा. Is it polynomial or it's not polynomial? What is the algorithm that will give you polynomial? Linear algebra.
All the variables are
No, the variables are unknown. We are trying to find the variables. So you guys should do a bit of optimization before coming to the next class. Sure. So you think it's polynomial? Seems like it's polynomial. So you look at what is a simplex algorithm, what is a ellipsoid method. These are some methods that are used for optimization in linear constraints, linear, even in convex as well, and check what the time complexity is. Oh, the duality is also important. We'll use that heavily in the next lecture. So I hope you guys do a bit of a prep before. Okay. So now the idea is it seems like it's easy to compute. There are a bunch of linear equations that you have to solve. But now let's look at this game, the game of prisoner's dilemma. Now I'll tell you, you have what is the Nash equilibrium here, or the dominant strategy equilibrium, or whatever. Everybody is remembered it. Now if I want to compute the mixed strategy, what will I do? I'll again do the same exercise. I'll assign a probability P for C and for the player 1 and Q for player 2. And I'll go ahead and write these equations. So if player 2 is playing C with probability Q and 1 minus C with 1 minus Q, he's playing NC, then this is the utility that player 1 is going to get by playing C. I hope I'm correct. Please verify. And this is the utility that player 1 is going to get by playing UIC, UI, is it? NC, comma, Q. Am I wrong?
Probability is coming as negative.
Yes, I think I've written it correctly. Yeah, the probability here is, yeah, that's the idea. The idea is that probability is coming as negative. Q is coming as negative. So to ensure that player 1 randomizes, player 2 must play C with probability minus 1 by 4. Can it do? So what's gone wrong here? So intuitively, yeah, what has gone wrong in this argument? Why in this case? Why? You're correct. Sure, it is correct. It is correct. But why in this particular game it's happening? There is we have seen all the games with pure strategy Nash equilibriums. Come on. Everyone had pure strategy Nash equilibriums. The crime game had n pure strategy Nash equilibriums. What is the characteristic of this pure strategy Nash equilibrium? No. More. Yes. So what is good for player 2 to do? Irrespective of what the other player does. It's always good for the player to play C and C. And so there is a dominant strategy in this particular game, right? So it is always good for player 2 to play one of the strategies, no matter what the other player is doing. So why will it even randomize? Right? There is no reason for it to randomize. So the idea is you don't have to only look for solve the n bunch of equations. You'll also to see what is the subset of strategies that I will be actually assigning positive probabilities to. I won't be assigning positive probabilities to all the set of strategies because there is a dominant, there is a strategy which is dominated. There is no reason for me to play that. I'll just eliminate that. And the remaining strategies, if there is no more dominated strategies, I will randomize. So this characterizes more formally what constitutes a mixed strategy Nash equilibrium. So this gives us what are certain necessary and sufficient conditions to define what is a mixed strategy Nash equilibrium. Any doubts here? So everybody has a mixed strategy to define, right? So the mixed strategy for the third player in this case would be to eliminate the third pure strategy because it's dominated and mix between the rest two. Given that he mixes between the rest two, what the others will do. You'll have to keep. It's possible that one of the mixed strategy dominates the other. That we'll see that. You had pointed out that before. We'll see that. These are linear, but once you know what these strategies are, now you define set of linear equations and solve. But how many sets of possibilities do you have to explore? No. I'll it'll be clear. If this fellow had, let's say, S1, S2, S3 up to Sn, and this fellow had T1, T2, T3 up to Tn, what is the possible strategies that could be? What is the subset? For every subset of strategies, it could try to randomize, right?
Yes.
Even if it's only two players, it will still be exponential. The number of strategies space it has to search over. Okay. In two-player, it is linear. Otherwise, it's okay. I'm only talking about the two. If you remember, I asked only for the complexity in a two-player. Three-player is even tougher. The equations also won't be. You're very tough. Okay. Any more doubts? So let's move ahead. Row player is indifferent among the actions for which she assigns non-zero probability given a mixed strategy of the column. This is the assumption which is flawed. So the row player is not indifferent because there is a dominant strategy. So now we have to come up with so what is known as the support of the mixed strategy Nash equilibrium. Support is essentially the set of pure strategies that will have strictly positive probability. That's the support. So for the support is defined for the mixed strategy sigma. The set of the pure strategies, which is denoted by delta. So delta for a particular agent I, delta of sigma I, is set of all those strategies for which the probability it assigns is strictly positive. That is the support of this particular mixed. So the support of a mixed strategy is the set of pure strategies. The set of pure strategies that has strictly positive probability. So in the coordination game, the support was for the mixed strategy Nash equilibrium. The support was the entire set of pure strategies that we had. But for prisoner's dilemma, the support was not the entire set. It was just one of the dominating strategies. That's the end. Support for the mixed strategy Nash. I'm not talking about support for any strategy. You could define a mixed strategy with support such that it can be very expensive, but that may not be a Nash. Now this, with the help of the support and what the idea of mixed strategy Nash equilibrium, will define certain necessary and sufficient conditions. So if I tell you there is a strategy profile sigma 1 star up to sigma n star, how do you verify whether it is a Nash equilibrium or not? So to verify, these are certain necessary and sufficient conditions. So the first condition is that for every strategy that belongs to the support of this mixed strategy, right? So for every strategy for which the agent I assigns the positive probability, the utilities must be same across all those strategies. That is the first criteria, because that's how we have defined MSLE, right? Initially, when we were trying to find what the probabilities were, we ensured that the agent is indifferent to selecting any of the pure strategies. If one of the pure strategies gives me more probability, I'll just stick to that. Right? There is no reason why I will randomize. So for every strategy that I'm assigning a positive probability, I should get the same utility across all those strategies. And one more condition is that for every strategy that is not there in my mixed strategy, or I'm not assigning positive probability, the utility that I should get from those should be strictly less than that. It should be a dominated strategy. So I'm not assigning any probability to a particular pure strategy, then it should be a dominated strategy. If there is no dominated strategy, the utility that I get out of playing that should be same across all the other strategies for which I am indifferent. Should be indifferent to all the strategies for which I am assigning positive. So these are the two necessary and sufficient conditions for. So whenever I give you a strategy proof, I give you a game, I give you a strategy profile, and I ask you to verify whether it's a Nash equilibrium or not. You have to just plug in these two conditions and check. And if it works, then it's a Nash equilibrium. MSNE, otherwise it's let's see.
So it's probably for all sigma minus I.
No, dominated. If there is at least one other strategy that dominates this, then it's a dominated strategy. Only way for dominating, it has to be the case that no matter what the other is playing, it should dominate every other. But for dominated, as long as there is one strategy that dominates me, I'm dominated. Regardless, okay, that is it. So that's not the case. So it's not regardless of what others are playing. I fixed the other strategy, sigma minus R star, because I'm looking for the in Nash equilibrium context, I'm fixing everybody else's strategy.
It's not wrong.
Normal, sure, my bad. It's not exactly dominated in the sense that irrespective of what the other ladies are playing, but if they are playing this particular strategy, then playing SI dash is not good for somewhat. You're right. It's incorrect to call this a dominated strategy by our definition. Lot of confusion. Okay, any other questions, doubts, comments online? Okay, let's go ahead. So each player gets the same payoff given any pure strategy that is in the support or is assigned positive probability. And the player is indifferent about which pure strategies. So the idea is the utility is same for all the pure strategies that they are in that are there in the support. And then okay, the second condition I have not, and it has to also get strictly, not strictly, but at least as much utility as one of these strategies that as one of the strategies that is not in the support. So if there is a strategy that is not in the support, then you are not getting enough utility of it. That's the idea. Okay, so if I want to find mixed strategy Nash equilibrium in this particular game, right? So first, what I will try to do, so what would be the supports of each of these players? So what I'm essentially trying to ask is there any strategy that is dominating? Yeah. Okay, one of these strategies that is dominated is Z, because 0, it's 1-1 for both the X and Y and zeros for here, so it will never play this. Right. Now focus on this. Now is there any strategy that is dominated? Is there any mixed strategy that you can use so that one of these strategies is dominant? So if player 2 plays X, what will player 1 play? If player 2 plays Y, what will player 1? Will player 1 ever play C?
No.
So the idea is if player 1 decides to play A with half probability, B with half probability, then it will strictly get 1.5 and 2, which is more than 1. So this is what you were asking the other day. This is what I'm trying to say, that there exists a mixed strategy of A and B, that player 1 can play, which will strictly dominate the strategy C. Player 1 is never going to play C. C is also out of the picture. Now the idea is there's no more dominant strategies. Now you'll have to do the mixed strategy computation. P's and Q's and evaluate and things like that. So it's essentially for the second player, it's all one. Okay. So for the supports, B is strictly dominated, C is dominated by mixed A and B. So delta of agent 1 for the mixed strategy. So essentially for any mixed strategy Nash equilibrium, the idea is the support would be A and B, and delta 2 for any Nash equilibrium would be C. Now that you have fixed it, you'll find P where it is like this. P is essentially any value from 0 to 1 because second player is getting 1s everywhere, so it doesn't matter what the other player is. But Q has to do 4 by 7, so that player 1 runs. Okay, so whenever you are given a game matrix, first look at if there are any dominated strategies or not, remove them, reduce the matrix as much as possible, and then do your P's and Q's. Otherwise, what will happen is you will end up with negative probabilities and
P is for which strategy?
Q is for agent 2 and P is for agent 1.
Okay.
So in the grade of sometimes what it is,
Yes.
and it's
Yes. Yes. So now let's revisit the computation part of it once, how hard it is to compute. Right? You were all saying it's polynomial bunch of equations, solve it no, in two-player games. So the idea is, first you'll have to fix what your supports are. So now, what could be the possible supports for agent 2, agent 1? How many supports could it have? Essentially 2 to the 2 minus 1. All possible subsets of its strategy. And minus 1 for the empty set. Empty set is not my strategy, one of the strategies. So it's all possible subsets minus the empty set. Which is essentially, I could either choose A, I could choose B, or both A. That's my set of possible strategies. Similarly, player 2 will have 2 to the 3 minus 1, which is x, y, x, y, x, z, y, z, z, x, and x, y, minus the empty. What is the total possible supports for the strategy profile for the Nash equilibrium that you are trying to find? So if player 1 chooses this to be the support and assigns 0 probability to the rest, and player 2 chooses positive probability to this and 0 to rest, you will get AX as your strategy profile. Similarly, AY, AZ, all possible combinations, which is essentially 2 to the 2 minus 1 times 2 to the 3 minus 1, which will be 21. So this is nothing but 2 to the cardinality of the number of strategies that S1 has times 2 to the cardinality number of strategies that S2 has. And for each of these possibilities, you will have to check if it's some Nash equilibrium. You'll have to compute the P and Q. And if it works, it works. If it doesn't work, you'll get some negative numbers, discard that profile. Check for this, discard that. So you'll have to do a search over. So every search will not take a long time. It will be polynomial, but you'll have to do a search over a space of exponential number of possibilities. So computing Nash in general two-player games is hard. even so 3-player, it will be even harder because it's not even a linear equation that we'll get. We can discuss that in the next lecture. But yeah, for now we'll have to understand that even so, I guarantee we have not yet established the fact that such an equilibrium will always exist. First idea is to establish. I'm telling you that you can take it for a fact that an equilibrium will exist. Even if I tell you that it exists, computing it is hard. So existence is good. Typically in hard problems, the existence is. That's how you define the class NP hard. But this is not NP hard because you know it exists, but it's still exponential. So there is a different class of complexity for computing Nash equilibrium, which is PPAD complex. We'll discuss all of that in subsequent lectures. But the idea is it's a hard problem to find the Nash. So in reality, if you're playing a game and you assume that you will find the Nash equilibrium, then you are really lucky. Might not. It's a hard problem to solve. So the exponential algorithm, there is an algorithm to find out what is a mixed strategy Nash equilibrium in 2-player games, and that's called Lecture6. It's an exponential algorithm. In worst case, I won't be covering that. It's a very complex algorithm. But if you are interested, you can check this out. It's pretty famous. And then, but there is one positive side to it, and that is if the games are zero-sum. So what we have seen is 2-player general games, not zero-sum. But if I guarantee you that I give you a 2-player game and it's a zero-sum game with strict competition, then there is a polynomial time algorithm. We will look at that in the next. And for that, you will need to brush up your optimization a bit and learn and come what strong duality is. And then we'll use that to prove what is the polynomial time algorithm, how you can solve zero-sum games and find mixed strategy Nash equilibrium in polynomial time. Yes, the strong duality. If you, because next class I already have a lot to say. I don't think I can give an introduction to that. Let's see. Okay, we are almost ending. So what we have seen till now is what are mixed strategies and how to compute how do you define the space of mixed strategies, the capital delta SI. We also saw how you define utilities when there are mixed strategies using the theory. Then we saw what is a mixed strategy Nash equilibrium. When do we ensure that the other agent randomizes? And then we saw that the other agent won't necessarily randomize on the all possible pure strategies that it has because of the presence of dominated strategies. So we will have to explore all possible subsets and then try to find what is the Nash. So Nash equilibrium even for 2-player games, general 2-player games is hard. And Lemke-Hausen is the exponential algorithm that we have. But if I say there is a zero-sum game, it's guaranteed you can find it quite easily. And we have to also see that why MSNE always exists. So all of this we'll see in the next class. So today I have to just introduce 3 more simple terms, and I want you to revise these terms as well, because for the 2-player zero-sum games, we'll be using these max-min these notions to essentially find the mixed strategy. So what is max-min? Max-min value was nothing but my security value. It's the minimum value that I could guarantee no matter what the other agent is playing. So we can define a max-min value and a max-min mixed strategy. So given a strategic form game, this is my mixed strategic form game. The max-min value of the player I is given by this particular, so it's VI analyzed, where the other agent is trying to find the minimum overall possible So what is the minimum value that I will get given that the other player is randomizing over his strategy? So sigma minus I belongs to a set of all possible strategies that the other agents have, mixed strategies that the other agents choose, except me. That's what this notation is for. And I'm trying to find what is the minimum out of all those. Now I will play a strategy which maximizes the minimum. That's when I'm guaranteed to get at least that much value. So that's my maximum value. So for all possible mixed strategies that the others are playing, what is the minimum that I'm going to get? And what is the maximum of all the strategies that I have, all possible mixed strategies that I have? So this is the maximum value in a mixed strategy. So almost the same definition, it's just the space that we are searching for is different. And that makes a lot of difference. That also tells you why, if you were just searching in pure space, pure strategy space, existence of, okay, probably jumping. The idea is that having mixed strategy helps the existence of equilibrium concept. So here we are looking at the maximum. Similarly, we can define the and any mixed strategy that guarantees me this value is a maximum mixed strategy. And similar to the previous case, we can see here as well that my mixed strategy Nash equilibrium will guarantee me at least the maximum value. Similarly, we have the other value, which is the min-max value, wherein we just reverse the order. This is the value that the other agent is trying to force on me. No matter how hard I try, I cannot do better than this. So if the other agent is playing a strategy, if all the other agents together are playing a mixed strategy sigma minus I, so what is the maximum that I can get? And all the other agents are together trying to minimize the maximum that I get. So that's the min-max value. And just like and any strategy that guarantees me at least the min-max value is a min-max mixed strategy for the group. And just like before, we have the three things that is guaranteed. One is that given a mixed strategy Nash equilibrium of the game, my utility is at least the min-max value, and my min-max value is at least the maximum value. So the value that other agents are trying to force upon me is at least my security. They cannot force me to lose my security. So min-max value is at least the maximum value, and therefore, my MSID will also guarantee me the maximum value. Okay, these three things, the proofs are almost similar to the ones in the pure strategies. You should go ahead and try to prove these things if you're able to. But one more interesting thing that is here in this, which is very specific for mixed strategies, is that in two-player strategic form games, the max-min mixed strategies is equal to the min-max mixed. So values are the same. So, and to prove that, we need strong duality, and we will see it in the next class. So any doubts, any questions?
Yes, calculation wise, Q equal to -1/4 is coming, but probability being negative, I am not able to fathom.
Oh, that's because there is one of these strategies that is dominated. You're talking about the business dilemma, right? There. This one, right?
Yes.
So here you're assuming that I'm going to, so player one, there is no reason for player one to play NC. About reverse the entire. So there is no reason why player one will play NC, right? With any positive probability.
Correct, because it has better payoff.
Because if player 2 plays C, player 1 will
will
play,
never play NC.
yeah, player 1 will play minus C. And when player 2 plays NC, player 1 will still play C.
NC. Sorry, C.
Right. So by equating, what you're essentially forcing is that player 1 should get equal utilities from both. But that is not going to happen because no matter what, player 1's utility here is more. So there is no way player 2 can equalize the utilities across these two strategies. Because
Player 2 cannot force player 1 to play NC.
yes.
Okay. Then, but what we are essentially doing by equating these two?
We are trying to force that the utility that player 1 gets from playing C is equal to the utility that it gets by playing NC.
Which is not the case.
It is not possible, right?
Because in both the cases for NC, it is getting a lesser value.
For one of them, it is getting a lesser. Yeah, for NC, it's getting a lesser utility.
Then why we are equating at all?
Yes, we shouldn't. That's the exact point that I'm trying to make. That you should first identify what are the set of these strategies where you should equate. You cannot equate for all the strategies.
Okay.
So that's the next slide, wherein I say that we define something called as the support. So support will tell me what is the set of strategies where I should equate. And whenever we, essentially support is defining the set of strategies where I should ensure that the utilities are same across all these strategies. And therefore, I assign positive probabilities to these and no probabilities to the strategies that are not in my system.
So how this is being violated in prisoner's dilemma?
So in prisoner's dilemma, the support of agent 1 for any Nash equilibrium. If the agent 1 has to play an equilibrium strategy, then the support should be only C.
Correct.
So sigma 1 star of C should be positive, and sigma 1 star of NC should be 0, which means 1. So should not play the strategy NC. The support is only for C.
Yeah, support for sigma 1 star equal to only playing strategy C. Then sigma 1 star C is greater than 0. And why this is greater than 0 and why NC is equal to 0? Because it is not playing.
It's not in the support.
Correct.
It's not in the support or the probability with which it plays. It's not assigning any probability to it.
Similarly for player 2, it would be?
Yes. That's because this is a dominant strategy. Strongly dominant strategy. So the same argument will also hold for player 2.
Yes.
Won't have NC in the support. We only have C in the support for any equilibrium.
Okay. So please, can we move to next slide?
Yes.
Where the question was? Yes. So this is the criteria basis which we are finding the support and then equating.
Yes.
So suppose it was some other matrix, say 3 cross 3 or anything else.
I gave an example of this matrix, right? So in this matrix, there are so many possible supports. Right? So for agent 1, what are the possible supports?
Yeah, we calculate 3.
Yeah, A, B, and AB, right? So we have to check for each of these supports. So this is an assigned problem set problem. So what you have to do is that you have to first see that there is no pure strategy in Nash equilibrium in this. So all these supports are gone. Even this. Nobody is going to play pure strategy. You have to only compute the mixed strategies whenever both of them are randomizing. Yeah, so in this game, what you have to essentially find is what are the different possible supports, and for each possible support, you'll have to compute P and Q. If you are getting negative values, then you know that that support, that particular set of profile that you have taken is definitely not in the support. You have to move to the next. Yes.
So, I mean, is this a manual process or algorithmic process also?
You can write a code for it,
Okay.
but it will, in the worst case, it will take exponential time in the number of steps.
Can we go back few slides earlier? No, no,
This,
no, back. Where the condition, this necessary and sufficient condition.
oh, necessary and yes, these.
No, what is the meaning of the first condition?
Oh, okay. I'm sorry. So the idea is that so whenever there is a strategy that is in your support, that means you're assigning positive probability to it. So for all those strategies, if you fix that the utilities that you get, given that everybody else is playing sigma minus I star, is the same. Only then this will constitute a Nash equilibrium. Otherwise, this won't be a. So for a particular strategy profile to be a Nash equilibrium, so there is as an agent I am assigning some positive probability to a bunch of pure strategies. So for example, delta of sigma I star could be A and B. I had three strategies, A, B, C, but I only assign positive probability to A and B. So what it essentially is telling me is that since I'm assigning positive probabilities to both of them, and I'm not deterministically picking any one of them, then I essentially indifferent to both of them. That means the utility that I get when I play A, given that everybody else is playing sigma minus I star, is same as the utility that I get when I play B, given that everybody else is playing sigma minus I star. So I should be
Even though their probabilities could be different. I mean, choosing A or B.
The fact that I'm indifferent is not dependent on my probabilities, it's dependent on the other's probability. So whenever sigma minus I star is fixed, there is some utility that I will get out of these. And they will ensure that my probabilities are my utilities are the same. That's when this will be a equilibrium profile. Otherwise,
Okay.
as long as it is in my support. That's the first condition. The other condition is that the utility that I get by playing A should be more than the utility that I get by playing C, because C is not in my support. And similarly for B, even B should be giving me at least as much utility as C is. This is the other condition. So whenever there is a strategy that is not in your support, then it is not good enough. The utilities that you are getting out of the strategies that are in your support is more than the utility that you are getting by playing the other strategies, which is not in your support. So that's the second condition that you need to check.
Okay, got it.
So that's it for today. Any doubts, questions you guys can ask? Otherwise, we can do it. Thank you for coming on the panel.
So we have our midsem on June 9th.
Okay, sure.
So will we be getting any mock quiz paper before that?
Okay, so I can probably set your assignment like that, maybe similar to what your midsem is going to be. Is that fine?
Yeah, assignments is one thing which will be like, and mock, we usually get mock paper before the quizzes, so that to understand the pattern and how it is going to be.
So I'll make sure that the assignment one that you are going to get is the same pattern as your exam paper, midsem paper, so that if you solve your assignment once, you know it's sort of like a mock.
Okay.
Something like a
I think you'll get an account created in their portal, and you'll have to submit your assignments there. It will be MCQs and numericals. Won't be any.
Even ID students will get their accounts.
You should have taken it to the next one. Okay, whatever. So, any more questions, doubts, concerns?
Yes, ma'am. Can you hear me?
Yes, I can.
Ma'am, the date for the mid-semester, Professor Nilthara Mishra announced it in the other chat space. Does it apply for this subject as well?
Yes, the midsem is the same. Okay. There are two different exams. So the midsem will start on the day she has announced, but
Okay. And so the second question is the assignment that you will release. Will
yes.
it be on the portal? Will it be auto graded, or will it be a subjective manual evaluation that you will do?
So the plan is that your exams are auto graded. So I'll try to keep the assignments also the same.
Okay. Okay. And as far as the exam is concerned, any update on the logistics of that, like which portal will be using?
I have. So I will update all of that to you in like 2 days, if you wish, because I have to figure that out. And I'll also tell you when your exam will happen.
Okay.
Exactly.
Okay. Sure, ma'am.
Okay.
No, ma'am confirmed that 9th June is one exam.
Okay. I'll tell you when your exam will be. I have to talk to Neil and others.
Okay, there could be different dates. Okay.
It should be different dates or different times.
Then we have assignments as well, right? So where we get the assignments to fill in?
I have not been prepared your assignment. So I will prepare it similar to your exam, and I will let you know where it is uploaded. I'll send a mail to all of you.
Yeah, it was told that it will be integrated to our IITM portal, and there only we can do that.
Yes. It will most likely be there.
Okay.
Okay, in that case, I just wanted to point out one thing. The previous terms courses have still not been cleared. Like the portal has not been updated since this term, after the registration has happened. So if that has to be done, then I think that IITM should they should like work on it fast. Yeah.
So that is for IITM.
I'm not sure.
Yeah. Okay. Okay.
These logistics, I'm not sure. I'll just give them the assignment, and they will tell me where they have. Yeah. So wherever they are uploading it, they'll let me know, and I'll let you know. So I'll make sure that you guys get the assignment and you do it, because you're going to be graded for it. So don't worry.
Okay, ma'am. And one more doubt is, I think towards the beginning of this, towards the beginning of the classes, you mentioned that the assignment problems will be from the problem set that you have already given.
I'll keep it around that, but now since I have to make it objective, I'll have to change the question slightly so that it has. I have to sit in, solve the answers, and give you 4 options and all of that. So it will take a bit of time, and it will be similar to this. But definitely the problem sets that I have given are a bit more involved and complex. You can expect slightly easier Like based
So
on whatever I have taught. Yeah, it's going
okay,
to
ma'am.
just
So
yes.
will you be sharing the solutions to the problem set? Because if you're working some
So
of the
you
problems, you
actually
have to get an answer.
the idea is if any one of you has solved the problem set, it will be great if you can upload the solutions. And if you have any doubt on any particular question, I can sit and verify the solution or at least give you the solution. But right now, I think if I have to sit and give the solutions, it will take some time. Maybe 2-3 weeks of delay. So after 2-3 weeks, I can give you the solutions. But by then, I I expect you guys to figure out what the answers are. If you get good and fine. Otherwise, I can come and verify it for you. If you
Okay, ma'am.
have doubt on any particular question.
Okay, if not the exact solution, would it be possible for you to share the answer, like the final answer at least, so that whatever we have worked out so far, at least we can verify that way whether we are correct or not?
Okay. I don't have the final answers with me. That will take me some time.
Okay.
I can share it with you, but it will take some time.
Okay, ma'am. Yeah, I'm just letting you know about this thing because if we have at least the answers, we can cross check whether we are correct or not.
A lot of you have solved, so you can probably discuss and get an answer. And wherever you don't reach a consensus, you can ask me if the answer is correct or not. Because most of the
Okay, ma'am.
questions are straightforward. There are some which are open to discussion. So yeah, that we can discuss.
Okay, ma'am. Yeah, thanks.
Yes, welcome.
We are already running a tight schedule, but it would have been great if we can schedule one extra session where
Okay.
we discuss these problems. Maybe not all together, but the few tougher ones.
Okay, please. So weekends are fine. You can take because since you guys are probably working, you would prefer a slot in the weekend.
By any chance, you coming to Paradox?
No. I'm not associated with.
Because otherwise, it would have been great thing to schedule a class there itself.
Oh, no. So there is no plan of me attending Paradox in any way. I don't have any holidays for that. So what you can do is I can take an online session for all of you guys. Maybe the next. I think there's one more class that I need to take on Monday. So
Yes.
Tuesday,
Tuesday.
and then there is 1 week of gap. So these the timing 10 to 12. If it works for you, we can take any one of the days and have a discussion. Or if you want it in the weekend, we can do it in the weekend. 10 to 12. So you guys fix a timing and tell me. I'll tell you if I'm free, we can have a session.
Okay. Okay. So that means even during Paradox 10 to 12, you will be mostly available.
If you tell me beforehand, otherwise.
Understood.
Madam, there's a doubt regarding the pure strategy, Nash equilibrium, and this mixed one. In the pure case, we call it as a steady state one, so solution, and there is a possibility of cycles also happening if there is no equilibrium in the pure case. But in the mixture case, can we claim it is an unstable one because once player, let's say in the two-player case, the second player has a probability of 0.75 and 0.25, and if you want to get a randomized approach for player A, then then it may not be possible, right? It can go on in cycles. Let's say if based on the probability of B, A can choose a different probability, and again B will have a different probability. So is it possible to reach a steady state in the case of mixed one?
One is there won't be mixed strategy and equilibrium exists. So the steady state wherein people stick to a particular probability, which is an equilibrium state, will exist. That is what we will see in the next class. We will see that it is possible to reach to a particular, not next to next class, wherein it is possible that both of them are playing a certain mixed strategy and nobody has an incentive to deviate from the mixed strategy. That is possible. That will always exist. But that did not exist, like you said, in the pure strategy case, and there were cycles. That is true. But here it will always exist. And this also is a steady state because they are going to stick to their probabilities over time.
Okay, thank you.
Okay, let me. How do you do pattern?